I'm going to talk about geological time, and because I'm a geologist, and I think being here this morning, I think geological time to you guys might be like sort of distance and space, or light years is to me. So it's a really interesting concept to get your head around. But I'm going to take you back 100 million years to what the Antarctica was like 100 million years ago, and then bring you forward to today. So I'll start off with this slide, though, because this is why we work in Antarctica. Our headquarters are in Cambridge. We're a research centre in Nurk in UKRI, because the Antarctic, particularly, this wonderful satellite map, is covered in ice at the moment. It's up to 4 kilometres thick. It's got 90% of the world's ice, 70% of the world's fresh water. And the real issue is that the ice sheets on Antarctica now, we are beginning to see melt. We always thought that they were stable, but we are beginning to see them melt. And that impacts everybody in this room, even you here, because sea levels are rising currently and partly is due to the melt of Antarctic ice sheets. And if everything melts in Antarctica, we may not be sitting here, but that's a 60-metre sea level rise. So Antarctica has a huge impact on the UK, even though it's remote and a long, long way away. And I thought I would put a satellite in because there's a lot of satellite involvement in Antarctic work. This is Cryosat, which is Cryosat 2, which is really important. And satellites today are giving us a continental scale view of Antarctica, which is really important because it is so remote. And most importantly, also, it can pinpoint where we need to go as field scientists to go and look at the most important places in Antarctica. So these satellites are really critical. And there's one plea now. We are in the British Antarctic Survey. We are changing the way we work to use a lot of autonomous vehicles to save on fuel, actually, from don't use aircraft and the big ships so much. And one of our problems is that we have a lot of data being produced by these autonomous vehicles, and we need new satellite technologies to send it back. Because at the moment, the quality of the data that we can send back is terrible because it's all decimated and pixelated. And we are really keen to talk to anybody who is working with a satellite company. We need satellite dishes in Antarctica to improve our communications and improve our data transfer. So if you're interested in that, please let me know. So Antarctica is a beautiful place now with all this ice around it, but millions of years ago, it was very, very different. And I'm a geologist. I've worked on ancient climates in the past by using fossil plants to tell me what Antarctica was like in the past and the rock record. And so what I'm going to show you actually is that Antarctica was forested with dinosaurs around. And when I started this many, many, many years ago, it was kind of a nice esoteric thing to do, to go and look at rocks in Antarctica. But now, of course, it's become a little bit more poignant, because in the future, if Antarctica warms enough, one of the things that might happen is that certainly around the margins of Antarctica, we may see more than just a few mosses and lichens, but we might actually see things that we recognize as trees or plants. And if you go to Antarctica, actually, one of the most common fossils in the rocks that are exposed are fossil plants. So the continent actually is that the point of the, oops, sorry, if I turned it off. There we go. The most of it is covered in ice, but there are places like this which are mountain chains, and the tops of mountains stick above the ice sheet, and there are some cliffs around the edges which are exposed rock. And if you look in those rocks, you will see fossil plants, which tell us that in the past, for many, many millions of years, Antarctica was a land area and it was forested. And those plants are there as fossils, waiting for me to collect them, or I used to do that. This is quite important. And the takeaway message from this slide is that Antarctica 100 million years ago, which is time of the dinosaurs, was a continent over the South Pole. So when I say that we find plant fossils in Antarctica today, in the rocks today, as fossils. People say, oh, well, that must be because Antarctica was a tectonic plate that was near the equator, and that's why it was warmer. But that's not the case. Geologists can very accurately say that Antarctica, 100 million years ago, that's when Antarctica as a continent moved over the South Pole. So that's really important, because if the rocks and fossils show us changing climates, it means that the climate was changing, not the position of the continent from then to now. And you can see this is what we call a paleogeography map. So geologists can tell where continents were in the past. You can see the outlines of continents, 100 million years ago, you can recognize a lot of them. But you can see that Antarctica was connected to Australia at that time. And actually, you can see it was also connected to South America at that time. So plants and animals could have migrated more or less all the way across from the North Pole, all the way down through South America, trotted across Antarctica into Australia. And it won't surprise you to know that we do find some dinosaurs and fossils that are common to many of these continents. So we are dealing with, I'm going to show you that it was a warm world with plants and forests, because natural high CO2 from volcanoes. But not now. So this is where I used to do my field work. So this is the tip of the Antarctic Peninsula. So I'll do it again. For some of you know I'm going to do this. If you hold your left hand up and you put your thumb up, this is your map of Antarctica. So this is the Antarctic Peninsula that points towards South America. Our station in Rotherham is at your knuckle on your thumb. I'll show you that in a moment. And then the rest of this area here is mostly ice, with where your nails are the Transantarctic Mountains. So this is on the tip of your thumb, where there are a lot of rocks exposed. You can see here, you need a ship to move around the islands. But the good thing about working in Antarctica is there's no grass and there's no buildings. And so what you see is just pure rock, and the fossils are there on the surface. And you can see, again, this is just a satellite image of the area that I've worked in, some of the islands off the tip of the peninsula, and the places which are brown are the exposed rock. And so you can see there's quite a lot of rock around, and this set of islands is where I've worked mostly. And here's a bad day in Antarctica for a geologist, because you can't see any rocks. So there's two of us in this tent for 2 or 3 months. We're just, it's fine, it's summer. And there are boxes of food and our clothing and first aid kits around the tent. And normally in the summer, it's 24 hours of daylight. And actually it's the wind that's cold. So on occasions there is no wind, and it's fantastic, except when it snows. And then it's really quiet and amazingly peaceful if there's no wind. And so, but we can't do any work, and we're usually very tired by then. So we're in there playing cards, listening to music, and eating a lot. But this is a good day in Antarctica for a geologist. So let's see if it works. You can see my field camp up there, around here, about 10 miles away. And these are sediments. They're rocks that are 100 million years old, but they're not actually turned to rock. They're in an unusual position that they are still soft. And in them, there are a lot of fossils. You can see me holding an ammonite there. So we have a whole suite of these fossils. So you can see at the top, you can see something that looks like a clam, scallop, bivalves that live on the seafloor. And then we can see amazingly preserved fossils, actually. The curly ammonite, which is like it became extinct with the end of the dinosaurs, but it's a little like a cuttlefish, if you like, and that's its shell. And then here we've got sort of gastropods or snails, if you like. And the shiny shell is really important, because that's the original shell material. And we can pick bits of that off, put it in a mass spectrometer, and we can work out from the composition of the shell, the temperature of the seawater in which it lived. And in the warmest times, we find it's about 15 degrees centigrade the temperature of the marine waters. And I work with an artist, or a couple of artists actually, because getting your head around what life was like in the past is quite difficult for for people who are not so sort of involved in it. So it's amazing. This artist, Bob Nichols, paints dinosaurs. That's what he does for a living. So he takes the pictures that I have in my mind, which I've gathered from all the information in the rock record, and he puts them on canvas for you to see. So this is probably what the seas were like in Antarctica. So in the background, you've got the Antarctic Peninsula. So that's the thumb, which was probably like the Andes at that time. This is 70 million years ago, but near enough. And then this huge beast here is a mosasaur. It's a big marine reptile about the size of a double-decker bus or larger. And that's eating a primitive shark. You can see in the ocean waters there, again, the curly ammonites. And there are fish, and there are lots of things on the seafloor. And then we've got bird fossils as well. So very productive ocean life. But also, if I go back, you'll see on the highlands, there are lots of forests, and all that material from the forests, wood, leaves, pollen, spores, and flowers, were washed into the ocean sediments, and then they were waterlogged and buried in the ocean sediments. So in that same suite of rock sequence, we also find these amazing fossils. So we have here leaves like this, or compressed leaves. So here's a flowering plant leaf. There's a leaf over there with those very, very distinctive veins or folds, which you will see later on. This is southern beech, Nothofagus, a very classic southern hemisphere beech tree. Pollen and spores here, beautifully preserved. And then fossil wood. So bits of those wood are about 1 meter in length. And they're petrified stone. So the fossils are petrified in nodules and beautifully well preserved. So the wood is here. So this is driftwood that drifted out from those forests, was waterlogged, and then sank into the muds in the bottom of the ocean. And over time, mineral solutions soaked into the cells and then crystallized to form, hard rock. So you use a diamond tip saw to cut up that wood, and you can make thin sections, microscopic thin sections, and you can see beautiful tree rings in the wood. And you can see in some of the rings there, very uniform in size, very distinctive. So these trees were growing very happily in a warm, wet environment. There was nothing that was really disturbing them at all. So the trees were very happy in Antarctica when they were growing there. Then we have leaf fossils. So there's a leaf fossil over there. You can see, again, a compression of a tree fern in that sediment. And all I'm going to show you, all the plants, are the ancestors of the southern hemisphere vegetation today. So the plants that grow in the southern hemisphere today are very different from what grows outside here in the northern hemisphere, by the way, that's due to plate tectonics in the past. So if you've been to Tasmania, New Zealand, South Island, New Zealand, or Patagonia, you will recognize some of these plants. So here's a tree fern, very common in New Zealand, and we have the fossils of them in Antarctica. And then these amazing ones here, in that nodule there, you can see a branch with these brown leaves sticking out. And these are almost identical. Well, they are identical, actually. The student was working on them, to monkey puzzle trees that grow today naturally in the high mountains of the Andes, particularly in Chile, but you find them in New Zealand as well. The ones you see outside here are brought back by Victorian botanists not millions of years ago, hundreds of years ago, from Chile. But we have a lot of monkey puzzle tree fossils in Antarctica. And there's a picture of the Andes in Chile, a fantastic area, the volcanic area, the volcano there, with monkey puzzle trees, and then southern beech in the undergrowth. All you need is a dinosaur, and you'd be back in Antarctica 100 million years ago. And I put this one in because many, many, many years ago, we were working out how to work on these fossil plants without destroying them. Because normally geologists chop things up and then make thin sections with them to look at a microscope. And then years ago, of course, tomography, neutron tomography, came into use for looking at fossils in rocks, which you didn't want to destroy. So actually, I spent some time across the road in the diamond light source to look at some of these plant fossils in 3 dimensions. And it's quite interesting because actually what you can see is a monkey puzzle stem, and it looks exactly like a monkey puzzle stem would today. So, but a really interesting way of looking at the whole fossil. So again, putting together all that information, here is the best reconstruction you'll ever see of an Antarctic forest, fossil forest, 100 million years ago. And I had a student who worked in Antarctica on a rock platform, a bed of rock in which there were tree stumps in place and rootlets of plants in place. So she measured everything very accurately. And this is exactly what she was looking at, reconstructed. So we have there over on that side, on the left side, you can see a ginkgo tree, maidenhair tree, which are very common today, but were very, very common in the geological past. And then there are, in the middle, there's a southern hemisphere podocarp conifer. You can see the monkey puzzle trees. You can see the tree fern. In the undergrowth, there are some plants which became extinct, and so we reconstructed them from the fossils. There are normal ferns. There's lichen and moss in the undergrowth. 100 million years ago, there were no flowering plants. They had evolved on Earth, but they hadn't reached Antarctica at that time. Very, very rare. So this is mostly ferns, conifers, and cycads, which were part of the sort of vegetation of the time. And I usually do this to school children, but I'll do it to you as well. So when we were working on this forest, we didn't see any evidence of bones for animals. We have seen bones elsewhere. So I asked the artist, Rob, if he would just put 2 eyes poking out under the vegetation, under the undergrowth, to just show that there must have been animals that lived there. And when he brought me this painting, it's an oil painting, it's in the Antarctic Survey in Cambridge now. I said, Rob, I'm disappointed you haven't put me any eyes in there. And he said, yes, I have. I've given you a dinosaur. Can you see it? It's camouflaged. It's there he is up there behind that tree. Look, there you go. So this is a 9-meter long herbivorous dinosaur that we actually now have found the remains of way up in the north there, where those volcanoes are. We found the bones of a dinosaur, which is actually that type, which also lived in Australia and probably lived as herds that wandered around, as I said, across the continents, and lived in Antarctica and also lived in Australia. So we had herds of herbivorous dinosaurs living 100 million years ago in Antarctica. Now, because we've got forests, it's not surprising that we also had forest fires that probably were just caused naturally by lightning. And we do have a lot of amazing fossils preserved as charcoal. So here's a picture of a charcoalified seed. And when things are burnt as charcoal, they're really amazingly well preserved because they don't rot and they don't deform, except they fracture. So they become very brittle and can crack. But otherwise, they stay perfectly intact. They don't decay. And so we can really we found these tiny seeds and fruits, which tell us a lot about the very small parts of the vegetation. So I had another postdoc work with me, and this, you see on the left-hand side, is one of these tiny fossils, charcoalified little seed or flower. I'll tell you what it is in a moment. I'll give the game away. A vessel. It's about a millimeter in height, and you can see it's a little vase or a cup with a cap on the top. So these millimeter-sized fossils, hardly anybody works on them because it's quite difficult. But Helena, who was a postdoc with me, she recognized this as the flowers of Myrtaceae family, which is now the gum trees or eucalypts. So these tiny fossils are telling us about the first flowers, the evidence of the first flowers that we found in Antarctica about 80 million years ago, which is really amazing to find fossil flowers. So, as I said, what we see actually are the early ancestors of the present Southern Hemisphere vegetation. So there on the top row, you can see that little leaf with about 2 centimeters long with the very strong veins, southern beech, Nothofagus. There's a modern one down below, and that grows everywhere in the Southern Hemisphere, low in the high latitudes. The middle one is Embothrium or Proteaceae. So actually, if you go into somewhere like Marks and Spencer's now and you buy a bouquet of flowers, you can see these big, really waxy flowers. These are Proteaceae they usually come from South Africa to Marks and Spencer's, and that we had those in Antarctica at that time. And then that kite-shaped leaf, which is a bit more tropical, which grows in Australia today, also we have that in Antarctica. So eventually flowers did appear in Antarctica, so not 100 million years, but they did appear about 80 million years ago. So this is a reconstruction by another artist to show Antarctica a bit later on. So you've got the Andes type mountains in the background with the monkey puzzle trees and lots of ferns and mountain floras up there. And then all the lowland rivers, we know it was very wet from the sediments. We've got southern beech trees, Nothofagus. You can see the red dots up there, that's the Proteaceae flowers in there. We've got water lily type plants around the rivers and a lot of small heath plants in the background. In here also is dinosaurs. So my Argentine and American colleagues work on the bones that we find in these sediments of 70 million years old. And we've got things like the big sauropods, vegetarian sauropods. We have over in the distance over there, we've got the hadrosaurs that make, if you're a Jurassic Park fan, they make the hooting noises with great big so cavities in their skulls. We've got a kind of T-Rex type creature over there. And then we have real birds in the foreground in the pond, but we also have avian type dinosaurs, raptors. So at 66 million years ago, the dinosaurs died out, but not the avian type dinosaurs. They became birds. So when you hear somebody say all the dinosaurs died out at the end of the Cretaceous, 66 million years ago, that's not quite true because a lot of them remained and they evolved into what we know as birds. So once the real dinosaurs, the non-avian dinosaurs had died out, Antarctica and the rest of the world became a different place because that, as you may know, gave rise to space for the mammals to evolve. And the same happened in Antarctica. So 50 million years ago, Antarctica looked like this. So this is the island where I showed you my campsite and where there were marine sediments. This is exactly the same island. So in younger sediments, we find the same plants. So there's Nothofagus over there. There's monkey puzzle trees. There's some flowers, Winteraceae, Southern Hemisphere, which again we find still. So nothing happened to the vegetation when at the end of the Cretaceous, when there was supposed to be a meteorite impact, but the animals did change. So see, over here is a possum. So we had possums, marsupials in Antarctica. We had these sort of elephant-looking things, the ungulates, hoofed animals, are things called Gondwanatheres, which eventually became extinct, but I like to think of them as sort of early stage llamas. And you can see that bird behind the tree trunk there, which is a rhea or a carnivorous bird. So there are fossils of large birds around at this time. And the other interesting thing is in this picture, which is painted by scientists from the American Museum of Natural History, you can see on the beach there are these little black things here. And these are penguins. So we find fossil penguins of 50 million years ago in the same layers of rock that we find all these leaves and these animal bones. So penguins evolved when Antarctica was warm and somewhat tropical. Penguins did not evolve in the Ice Age, which is a big surprise to most people. And in fact, when penguins did evolve, they were enormous. They were giant size. So there's an Argentine colleague of mine, Carolina, and she works on fossil penguin bones. And in these 50-million-year-old sediments, she finds a whole range of different penguins, from very small ones, but also giant-sized ones that are over 6 foot tall. So, and actually now penguins have been found on all the continents, southern continents. The penguin fossil bones have been found of giant penguins. So it wasn't just Antarctica. So here's me standing in the Swedish Natural History Museum next to a big plastic penguin that has been reconstructed from a toe bone that the Swedish explorer Nordenskjöld found in the 1800s, when, early 1900s, when he was there. And he found the first remains of these giant 6-foot penguins that lived in Antarctica and on the other continents. So that would have been a pretty scary meeting, I think, if he'd met a 6-foot penguin. But they evolved, remember, they evolved in warmer periods. So what I've shown you all the evidence for warmth, but there was a change to Antarctica about, about 40 million years ago, or just before that, and both tectonic and climate. And we know that carbon dioxide levels were beginning to decline naturally, and the continents moved apart. So you can see here, this reconstruction shows that Antarctica is now isolated, particularly from South America. That junction from South America is absolutely critical. And for the first time, the ocean currents could flow around Antarctica. So you get the circumantarctic current. And that means that as the climate was cooling, ice built up on Antarctica, and then it got trapped in this icy tomb by the circumantarctic current. And some of those, particularly some of those waters that go in that channel between South America and the Antarctic Peninsula, it's called the Drake Passage. They're the roughest waters in the world. And that's why I'm going on sea training tomorrow, is because the ship is going across there in January and you don't want to fall in the water there, but it's pretty horrendous. But Antarctica then became cold, and it gradually continued to become colder from then. And everybody used to think that all the plants had died out at that point, but actually there were still plants in Antarctica that were found much more recently. If we go to really quite central Antarctica, only a few hundred miles from the South Pole, some geologists were working on these rocks here. This is the Beardmore Glacier, where Scott and Shackleton went up to try and get to the South Pole. And they actually, Scott and his men worked on the other side of the glacier, on the far side. If they'd worked on this side, they might have found these leaves and not the other ones. But then they walked back down to their deaths just a bit down the glacier. But a few years ago, some Americans were looking at these rocks here, and they discovered these small leaves in the sediments. You can see them there. I'm sure you recognize them. And so we went back, a group of us went back a few years ago now, and in these rocks, which are glacial tillites, so they're rocks that were formed by glaciers that are there, we found these tiny little twigs. So there is the last forests in Antarctica became very dwarf-like, but their remains are there. And then we found layers of these leaves, which you can see are these small leaves with a very clear folds in them, which are the southern beech, the fagus. So we gradually see the change in the vegetation as the climate became cooler. And this is about 5 to 10 million years ago. And this is probably what Antarctica looked like by that time, this is a picture of the high mountains of Tasmania, the same type of trees, a small southern beech, and a few sort of tundra-like heath plants, snow in the winter, and mean annual temperatures of about 3 or 5 degrees, which is what we predict for Antarctica at that time. So much, much colder climates by then. So now I'm going to just go on and bring you up to date with what's going on in Antarctica today to put it into context. So having gone through this beautiful warm Antarctica that gradually cooled, about 5 million years ago, the whole Earth became much, much colder. The ice set in Antarctica about 40 million years ago or longer, so quite a long time. But 5 million years ago, we had what I call the icehouse, when the whole Earth became much cooler and ice sheets grew on Antarctica and on the Arctic as well. So the Arctic ice is very, very young compared to the Antarctic ice. And the Antarctic ice sheet spread way, way across the continent. And now, of course, we went from that very, very cold period to now we are looking at what is happening to Antarctica as our climate warms again, but man-made warmth. And so the big interest is in what is happening at the fringes of Antarctica. And so here's a picture of Antarctica today. Here is our Rothera station there. So this is our main hub station, quite isolated on the Antarctic Peninsula. And on the whole, scientists tend to go to Rothera from Chile or Falklands and then go out in small planes to go out to the rest of the continent. And I should say, while I'm here, is that one of our mission, apart from doing world-class science, but also the other part of our mission is to be the UK presence in Antarctica. And if you would like to do any kind of research in Antarctica and you get funded by a UK or EU grant, then come to talk to us, because if you have a funded science project, we will take you to Antarctica and support you for free. So that's one of the roles of BAS. So if you'd like to do some research in Antarctica, do come and contact me afterwards. So what is happening to the climate today as the climate warms? And one of the things that we now know in the last couple of years is that the ice shelves around Antarctica are melting. So, and this is my favorite map from NASA, which shows the ice streams. So it's actually a velocity map, but what it shows is all the glaciers on the main land area of Antarctica are shown as these tree-like structures as the ice is flowing down the glaciers into the purple areas. And the purple areas are the ice shelves. So the ice comes off the continent and then it floats over the ocean for a while until it becomes unstable, and then it breaks up into big tabular icebergs. And the really important thing about those purple areas is they act like doorstops to stop the glacier ice, which is the ice which is going to cause sea level rise, floating, breaking up. Or stops the glaciers floating into the ocean. And we're particularly interested in even quite a small area down here called the Thwaites Glacier, which you may have heard about. So this was a big US-UK project, which is the last field season is now happening, where we used all kinds of instruments and several field projects to look at what was happening. In particular, we used ships to launch autonomous vehicles underneath ice shelves. We used to send a lot of instruments underneath ice shelves in the past, but they never came back. But actually, we've got to a really good state now where we send them under. They've got cameras on them, so we can see underneath the ice shelves for the first time. And they also come back and carry their data with them. And we work with satellites, we work with twin otters, we work with hot water drilling through the ice shelf, everything to understand what's going on. And we know that the warm water is getting, because the winds in Antarctica are warming because of climate change, the winds are blowing warmer ocean water underneath the ice shelves and melting them from below. And of course, if they weaken the ice shelves, then the glaciers may speed up and enter the ocean, which is causing more sea level rise. The other thing that scientists do, which is really important, is they're drilling into the ice sheets for the history of the ice. So here's a big field camp. These are like 10-year programs. setting up a big international project, drilling an ice core. You can see the meter-long ice core on the bench there. When they bring them back into the lab and they chop them up into these fine layers, so they're well dated. And then you can see in this slab of ice, you can see these tiny little bubbles in the ice. And this is the air that was trapped between the snowflakes when the snow fell. And over time, that air pocket is trapped in harder and harder ice. And it's there up to 800,000 years. Our oldest ice core at the moment is 800,000 years. So that's the original air that was on the Earth 800,000 years ago. It's the only source of original air for all of that time. And so this is produced from that work. This very famous graph has been produced, which I'll just talk you through it because it's really quite important. From zero today, back 800,000 years. So that's the time when humans have been on Earth, evolved. So we are really ice age animals. And from that ice, you can measure both the temperature, which are the brown line, and the CO2 composition in those tiny little air bubbles. And in BAS, we have the equipment to measure the carbon dioxide and greenhouse gases, methane as well, in the air bubbles in the ancient ice. And you can see that it goes up and down because that's the glacials or waxing waning of the ice sheets on Earth. But the real takeaway message from this is you can see that red line. And you can see that wherever the ice was waxing and waning over the last 800,000 years, carbon dioxide levels never went above 300 parts per million. We can measure that very, very accurately. But look where we are today. We're actually 421, I think, today, parts per million CO2. So we're way, way, way now above the stability of an ice age Earth. And the temperatures are trying to catch up with where the CO2 curve is, hence our unstable climate. This graph is so powerful. We've got it in BAS, and when we give tours to people, it's the one graph that people get, ministers and government officials, and they take pictures of it because it is so powerful. But we are way, way out of the stability of an ice age Earth. So that's why a lot of the weather is extreme and the ice is melting. So I'm going to leave you with that. But just before I finish, I'm going to show you a 2-minute video to finish off with, to give you a little taste of a wider range of what we do at BAS and to advertise BAS. And it should have a lot of music on there. Can we stop the video and play the music? Thanks. Can we play the music? Thanks. Can we start again? Thank you. Music is really important.
Music's gonna have to be really good now.
Yeah. It's I'll see if I turn it up. It's not loud enough, but never mind. Thank you very much.